Today we're going to be talking about Taylor and Maclaurin series.
A Taylor series is a way to accurately approximate the value of a function by taking its derivative at a given point. It is a series expansion around a point x equals a. The Maclaurin series, however, is much easier because at the given point x equals 0.
This will come in handy later.
First, let's review sequences and series. There are two types: arithmetic and geometric. In arithmetic series, there is a common difference and geometric series, there is a common ratio. Arithmetic series would look like this, with a common difference of 2, for example. Whereas a geometric series would have a common ratio, let's say 2, etc. To find the sum, there is a couple formulas that you should know. And for a arithmetic sequence or series, it is what this means is the first term in the series plus the common difference times the nth number of terms minus 1 is equal to a to the nth term of a. Now for a geometric series, it is similar but with a little twist. It is sub 1 plus r to the n minus 1 is equal to a sub n. This is because it is a geometric series, which means it is being multiplied by a number to get to the next number. That is why it is r to the power. Right now you may be thinking, wow, I clicked on this video to learn about Taylor and Maclaurin series. What does this have to do with that? What does this have to do with calculus? I learned this years ago. But to formulate a Taylor and Maclaurin polynomial, you have to learn the rules, which is similar to the geometric and arithmetic expressions. For a Taylor polynomial, you're going to use f to the nth derivative times a divided by n factorial times x minus a to the nth power. And for a Maclaurin polynomial, you're going to use f to the nth derivative of 0 divided by n factorial upside down times x to the n. Let's take a look at formulating a Maclaurin series for a different function. We know that the rule is f to the nth derivative of 0 divided by n factorial times x to the n will give you the term for the Maclaurin series. Let's take a look at e to the x, for example. Well, if you plug in 0, you're going to get f to the 0th derivative, which is just e to the x, divided by 0 factorial, which is 1, times x to the 0 is 1, so you're going to end up with 1. Now, if you plug in f to the first derivative, e's first derivative is e to the x, so you're going to be left with x. Now, if you plug in the second derivative, you're going to get the second derivative of e to the x times x squared over 2 factorial, so you're going to get plus x squared over 2 factorial. Plugging in the third derivative, e to the x, so it's going to be the same thing, it's going to follow a pattern, x cubed divided by 3 factorial, and x to the 4th divided by 4 factorial. That will go on forever. So now let's look at sine of x. Well, sine of 0 is 0, so the first term is going to be 0. You can choose to write it or leave it optional. It won't affect the value of the sum. Now when you plug in the first one, first derivative sign is cosine, then you're going to get 1, or x, then, because it's an alternating function, because sine differentiates to cosine, which then will go to minus sine, so you have minus x cubed over 3 factorial, then plus x to the 5th over 5 factorial plus x to the 7th over 7 factorial. Actually, this will be a minus. And that will go on forever. You can do this for any function by plugging in the derivatives and figuring out what this series will be. This is very helpful when you have a function that you can't differentiate, or a function that you can't integrate, which we will talk about much later. So I know those expressions may seem quite difficult, but I think it will be beneficial to look at it on a graph. So let's take the function f of x equals cosine of x. Everyone knows the graph of that. Starts at 1, goes down to pi over 2, then pi, and it goes down like this, up, and then like this. Nice valley shape. So if we wanted to use a Maclaurin polynomial, for example, it's basically like taking the derivative at every single point and adding them together. So you'd get a curve. So let's say if you took the derivative at this point, it'd be a line like this, and then you'd get a line like this, and then like this, and then like that. And it's just going to keep going on and on and on forever until it eventually sketches a curve that matches exactly to the cosine graph. That is basically what a Taylor and Maclaurin polynomial is doing, which is why it can give us such an exact approximation of the function values. For the sake of time, we're going to take a look at an example for a Maclaurin series, but I'm going to go quite in depth into it. So we already looked at cosine of x, so let's continue looking at that. So we have f of x is equal to cosine of x. Now we know for the Maclaurin series, we have the rule, which is f to the nth power of 0 divided by n factorial times x to the n. Now, let's just make a little chart to show you what it would look like. Cosine of x, so we have f of x equals cosine of x. F prime of x is equal to minus sine of x. F double prime of x is equal to minus cosine of x. F triple prime of x is equal to sine of x, and so on and so forth. Now we'll draw a little thing. We got f of 0, f prime of 0, f double prime of 0, f triple prime of 0 equals. So now we know that it's going to be like this. 1, 0, negative 1, and 0 again. So now the zeros, they're obviously just going to come out as 0, but you see you have 1 and negative 1, which means this is an alternating series. Now applying this to the rule, we can figure out that cosine of x will really be one. So if you plug in f prime of 0 divided by the f prime, or f to the 0 power, so it's just this, f of 0 is 1 divided by 1 factorial times 1 is 1, plus f prime of 0 divided by 1 factorial times 1. Well, f prime of 0 is 0, so that's not going to do anything. Moving on to this though, you have f double prime. So f double prime of 0 is -1. So instead of plus, this will be a minus, and n, so this is the second, so it's going to be 1 over, this is a 2 because it's the second derivative, factorial, times x squared. So this pattern is going to continue forever, and then you'll get plus 1 over, the fourth would be 1 over 4 factorial times x to the fourth. And that will continue forever. That will give you the value of cosine of x. Now that we've found the sequence for cosine of x, we're going to use a little bit different of a notation. We're going to change the notation into a summation. So I'm sure that capital sigma looks very familiar to most of you guys, but because this is going to be infinity, so we can find the full curve, this is going to be summation to infinity from n equals 0. Now we need to figure out what the rule would be. So we know that it's alternating, so we're going to have a -1 somewhere in there so we can get a negative. And because it's alternating, you're going to have it to the nth number of power so you can figure out which one will be negative and which one will be positive. So you have 1 to the n. Now we know that you're going to have an x there because you have x to the power of multiple different things in there. So you're going to have an x times x. And you know that just plugging in regular n is not going to get you the right thing, because if you plug in n equals 0, it's just going to leave you with x, which is not the first term. So you know that the first term has to be 1, therefore you're going to have something to the power. So is it going to be regular n or is it going to be 2n? Well, if you plug in regular n, you're not going to be left with 1, so you're going to have to put 2n. Now you see the factorials on the bottom. The second term has a 2 factorial on the bottom, so you're going to have a 2 somewhere in there, and you're going to have a factorial somewhere in there as well. But because the denominator increases by a factor of 2 each time, you're going to put an n. And now that's just not any 2n factorial, the n has to be in parentheses because it takes the factorial of the entire thing. Now you just formulated the summation for cosine of x. Now that we've formulated this expression, you may be asking, well, what happens if you have cosine of x squared, or x times cosine, something like that? That can very easily be changed to change the expression. So for example, let's take cosine of x to the fourth. Still going to have the summation from n equals 0 to infinity. You're still going to have the -1 to the n. When you plug in a to the fourth power, you're going to have to do that to where the x is. So you have x to the fourth times 2 to the n, all divided by 2n factorial. Great. Now you figured out x to the fourth. Well, what happens if you have a coefficient of x? Well, let's find out. X cosine of x to the fourth. Now you're still going to have the summation, n equals 0 and infinity. You're still going to have the -1 to the nth power. Now this is where it gets changed. Remember, when you're multiplying by the power, so this is really an x to the 1. When you multiply powers, you are really going to add them, opposed to taking the power to powers, you're multiplying them. So when you are multiplying powers, you're going to add them, so you're going to be left with x to the 8n plus 1, because this 1 comes from this x in front, and then you're going to be left with the denominator of 2n factorial. That is how you can do that for every single variation of cosine or anything like that. Now that we've found out the rule for the cosine of x and how to translate it to different types of cosines, we can finally get to the fun part, actually integrating it. So let's take, for example, the integral from 0 to 1 of x cosine of x squared dx. Now you may be thinking, well, how am I supposed to do this? You can't just do regular chain rule, or you can't just integrate cosine by itself because of that pesky x in the front. Well, you can use Maclaurin series to your advantage. Now we know that cosine of x is equal to the summation from n equals 0 to infinity of -1 to the nth power times x to the 2n all divided by 2n factorial. And we know now from our previous lesson that x cosine of x squared is equal to the summation from n equals 0 to infinity from -1 to the n times x to the 4n plus 1 divided by 2n factorial. Now you may be thinking, oh, that's perfect. We can just substitute it in. Exactly, you're right. That's exactly what we can do. So we can take integral from 0 to 1, the summation from n equals 0 to infinity of -1 to the n times x to the 4n plus 1 all over 2n factorial dx. Wow, that looks absolutely complicated, right? Well, this is actually very simple because you have to remember that n is always going to be a constant number. It will never be a variable. So to differentiate or to integrate this, it's just going to be similar to integrating a simple f of x equals x to the 4th. It'll be simple as that. So what it's going to be is this up here, you're going to add 1 and then divide by the new numerator. So you'll get, this is going to equal the summation to infinity from n equals 0 to -1 to the n times x to the 4n plus 2 all divided by 4n plus 2 times 2n factorial, evaluated at 0 and 1. Wow, that is much easier than you thought it would be, right? Now let's actually get to solving this by hand. Now you've come so far in solving this problem, we just have to get the final evaluation and see what our number is. So evaluating this is simple as using the first fundamental theorem of calculus, f of b minus f of a. And doing that, you already know plugging in 0 to this will get you 0, so what's the point of doing that? There is none. Plugging in 1, however, will give you a real answer, or a real expression, summation n equals 0 to infinity, -1 to the n. Plugging in 1 here, 1 to the any power is going to be 1, so this is just times 1, which is nothing, divided by 4n plus 2 over, or times 2n factorial. Now solving this, you're going to plug in some numbers. First you're going to plug in 0. Plug in 0, you're going to get 1 on the top, and you're going to get 2, a 2, and then a 0 factorial. It is known as 0 factorial is 1, so 2 times 1 is 1, so you're going to be left with 1/2, and it's an alternating series, so the next term is going to be negative. So -1 to the 1 is -1, so you have -1, and then you plug in 1 down here, you get 6 times 2 factorial, which is 12 factorial. This minus is redundant. 12 factorial. Alternating series, so the next term is going to be positive 1 over, plug in a 2, you get 2 times 4 is 8, plus 2 is 10, 2 times 2 is 4, 10 times 4 is 40, 40 factorial. And that should be plenty of terms. This would go on forever to get the actual function, but we're just evaluating from 0 to 1, so that should be enough terms. Now actually typing that in the calculator, because I know none of you guys can do 40 factorial in your head, you're going to come out with an answer that is equal to 0.4999. Now when you type in integral of from 0 to 1 of x cosine of x squared dx, you are also going to get 0.4999. However, the numbers that come after both of these are different, because these will not give an exact approximation until it is all the way to infinity, which is impossible to solve by hand. Thank you guys for watching. Please leave a like and subscribe for more math videos. If you need any help, please leave questions in the comment section below. I'll try to answer them if possible.